Everybody ready? Hello, everybody, and welcome to the Astro Show, the place to be if you're curious about the cosmos. I'm your host, Dr. Sam, the founder and executive director of Wyoming Stargazing. Here, you can pick the brains of astrophysicists, get advice from an aerospace doctor, learn what astronomers have to say about life, and find out what's happening up above your head, all in the same place. So join us every second and fourth Tuesdays at 6 p.m. Mountain Time on YouTube, Twitch, and Facebook. You can chat your questions on Twitch and YouTube, or you can call in using the information on your screen. And we'd love to hear from you, so give us a ring. In this week's show, we are going to chat with Hannah Fritza, a graduate student from the University of Utah, Department of Astrophysics. Among other things, Hannah studies X-ray binary systems, and we'll hear all about that later on. But before we do that, let's welcome our co-stars. First, aerospace doctor and founder of Orbital Biodesign, it's Dr. Danny Carroll.
Hey, everybody. Good to be here.
Hey, Danny. Good to have you back. Next, assistant professor of physics at the University of Texas at Austin, it's Dr. Nick Galitsky.
Hi, everybody.
Hey, Nick. And last, but certainly not least, author, journalist, and creator of the Space Tourism Guide, it's Valerie Stymick.
Hello, everyone.
Hey, Valerie.
Hi.
All right, everybody. Let's get this show going. I'm going to go right into Astro Advice, life advice from astronomers, astronauts, and other scientists. As always, I'll read you the quotation, and then the co-stars will have a moment to try to figure out who actually said this. So here we are. There are many ways to be an astronomer, so follow what you like to do and want to do. You are not just your H index, and you don't have to conform to what others have done or say must be done in order to make it. Be true to yourself. So that's the quotation, and I'm going to give you a picture of each of these four possibilities of the individuals who said them. A is Dara Norman, who is an American astronomer and a deputy director of the Community Science and Data Center at the National Optical Infrared Astronomy Research Laboratory. So Dr. Dara Norman is A. B is Gabor Basri, American astronomer and professor emeritus at UC Berkeley. And I'm gonna move us down to the bottom here so we can see everybody's names. C is Russell Allen Hughes, Hulse, American astronomer and recipient of the Nobel Prize for his discovery of the first binary pulsar star system. And by the way, this is an older picture of him from the 1950s, I think. And D, Dame Jocelyn Bell Burnell, also a picture of her when she was a graduate student, Irish astronomer and discoverer of the quasar. So just to recap, we've got A, Dara Norman, Dara Norman, B, Gabor Basri, C, Russell Allen Hulse, and D, Dame Jocelyn Bell Burnell. All right, co-stars, what do you think?
Could we go back to the quote, please?
Yes.
Okay, thanks.
Oops. There you are. Oh. You didn't see that. Nobody saw that. That's what you get when you put me in charge of doing the slides. Everything goes awry.
I mean, I'm pretty sure all three of us were going to pick A.
Of course you were.
Yeah, I had a really good feeling about that too. Weird.
About that. It's A. Dara Norman.
I like to think Dr. Norman would have agreed with this quote even if she hadn't said it, but that was my guess. So I'm glad that my instincts were right on this one.
Okay, all right, fair enough. Yeah, she is a really amazing woman. I had never heard of her. Our operations director, Maggie, did some research and found this quotation. And she has done amazing stuff with her career, as well as a lot of DEI work in the field of astronomy, which is super important. So we want to take the opportunity to highlight her and these other folks who have also done amazing things in the field of astronomy in their own right. So we're going to start showing pictures of all the individuals who we have queued up for the potential quoter for Astro Advice. So we'll give everybody a little bit of screen time who deserves it. Good work, co-stars. You all got it right. 1 point for all three of you. Nicely done. All right, we're moving along here. What do you actually think of this quotation? Tell me your thoughts.
I feel like for a general audience, you'd have to explain what an H index is.
I had to look it up.
So there you go.
Do you
What
all,
is it?
it's
Exactly.
yeah. So, but Nick, you know, right?
Loosely, although I don't actually know what mine is, but this is basically
Right.
a number that somebody came up with some time ago that measures your publication rate and your citation number.
Yeah.
And so it's a measure of both of those. Are you publishing a lot of high impact papers is how you do it. And for certain hiring, they care a lot about it. Because I'm an experimentalist, I don't publish as often, so it doesn't tend to be as prominent in my field. But certainly for theory or some observation, or depending on department and who's doing the hiring, it can be a decisive factor. Kind of like GREs or something, SATs at a lower level, right? It's some sort of reduce this person to a number to figure out their value for the field.
Right.
Like their impact,
There,
like a person, like a human impact factor.
yeah. But just based on publishing, right?
Got it.
So yeah, that does kind of put this quotation to perspective. Thanks, Nick.
Yeah, and I guess we got a group of people here and none of us know our H index. There you go.
I know mine. Mine is
Clearly we're
zero.
following this advice.
Yeah,
Mine is definitely zero.
mine is not zero. I actually know that a few people actually read my doctoral dissertation and have actually cited it. How often does that happen? They slog through over 200 pages, maybe, or they just went to the conclusion. Who knows? But mine's not zero. Anyways, what do y'all think of this?
I think philosophically, I definitely agree with it, even though I didn't know what the H index was. The concept of like being reduced to a single measure of your productivity and having that somehow equate to your worth to society, that doesn't make a whole lot of sense to me. Whereas being true to yourself, as this quote says, and figuring out what it is that you love to do, you're probably going to end up, if you're doing what you most love to do, you're probably going to end up contributing more to society, big picture, than if you're doing something that you don't love. So I don't know, my 2 cents.
Yeah, I'm right there with you, Danny. I think that's right on.
This is definitely how I feel, because I am in this company and often in the company of fellow space lovers, the least professionally accomplished in a traditional sense. But I count myself an astronomer, not a professional scientific astronomer. But I really like the idea that people can contribute to the field in different ways, and that there is no one right way to be an astronomer. And I hope that someone listening or watching hears that and decides to take their own path.
Yeah, I mean, and I definitely did that as well. I am not a traditional astronomer. My PhD is not in astrophysics or planetary science or anything like that. It's in education. I just love astronomy, and I've spent the better part of 20 years learning about it and teaching people about it. So yeah, put me in front of a telescope and take me outside, and yeah, I'm in my element. But yeah, I definitely didn't follow the traditional path either. Any other thoughts on this? Okie dokie. Well, let's move along then and take a look at Astro 365, this day and week in astrophysics history. So on this day in 1671, Giovanni Cassini discovered Saturn's third largest moon, Iapetus. And I must say, I think this is probably my favorite moon in the solar system. First, a little tidbit about this name, Iapetus. You may have guessed that it is it's in the Greek pantheon of gods, actually not one of the Olympians, but one of the Titans. So son of Uranus and Gaia, brother of Kronos, father of Atlas and Prometheus. And the idea is that Iapetus was the father of the human race in Greek mythology. And it was actually John Herschel who suggested that the moons of Saturn be associated with the mythical brothers and sisters of Kronos. And Kronos is the equivalent of Saturn, the Roman equivalent of Saturn in Greek mythology. So I want to bring up a picture of this moon because it is super cool. So for those of you who don't know, this moon has two completely different hemispheres. So one hemisphere is really brightly colored, and the other hemisphere is really darkly colored. So it's been called the yin and yang of Saturn's moons because of this difference in reflective material on one side versus another. And astronomers have been trying to figure out why for a very long time. One of the first theories was that the moon was actually sweeping up particles from a more distant dark moon, but just on one side versus the other. Another idea was that ice volcanism could have been, excuse me, could have been distributing dark material. And then chemical reactions were taking place with solar radiation to create this effect. But more recently, however, it's believed that it's actually due to thermal segregation. And that has to do with the fact that it rotates very, very slowly. It takes it 79 days to complete one rotation. And it's a tiny little moon. So it's rotating really, really slow. So the idea is that the daily temperature cycle is very, very long, so that the dark material can absorb lots of heat from the sun and warm up, and thus potentially sublimating any ice. So the dark stuff will actually look darker without the ice. And basically over long periods of time, that is what has led to one side being much, much darker than the other. It's still possible that there was an influx of dark material from an external source. And maybe that's actually what triggered the warming on one side, having one side that was just more absorbent than the other. But there's still some big question marks, but isn't it cool? And then that gigantic crater as well. So yeah, in 1671, on October 25th, Giovanni Cassini discovered this moon. The name Cassini may be familiar to some of you. There was the Cassini mission that went out to Saturn, not to the moon Iapetus, but to the moon Titan. And then the Huygens probe was launched from said Cassini probe and actually landed on the moon Titan, which is Saturn's largest moon, much, much larger than Iapetus. Titan's so large that it actually has its own atmosphere. I think the only moon in the solar system that actually has a thick atmosphere, or any atmosphere for that matter. So a little tidbit about Iapetus there. Co-stars, anything that you would like to add or say about Iapetus?
I
It's a good moon, but-
noticed.
No,
Oh, sorry. Go ahead. No, go
I
ahead.
was just gonna say it's not my favorite. My favorite is Miranda typically.
Miranda's a good one. Miranda has the really big ridge lines, right?
Yeah.
Yeah. What were you going to say, Danny?
I noticed there are craters, like as you mentioned, but there's no, like on our moon where there are ejecta, at least on this view, those are absent.
Yeah, so it seems like the surface is pretty young, right? It isn't either hasn't been hit by a lot of smaller chunks, or somehow the surface is being changed by some process. Because yeah, you would expect to see those ejecta lines from recent impacts or really old impacts, but there's none of that. And I think that's one of the reasons why volcanism was one of the leading theories for so long, thinking that that could also account for lack of ejecta lines and other cratering.
Well, I get the sublimation theory. What I mean, it really looks like it just went through, driving down the highway around Saturn, a cloud of bugs or something like, oh, geez.
Yeah, I mean, I wondered about like the direction that it's heading in its orbit, right, around Saturn. Is there any way that it could have just like gone through, like a comet cloud or something? And yeah, it is possible that it accreted material from something else. We still don't really know. But yeah, it does kind of look like it was a big like bug splatter on one side, doesn't it? I buy it. So theory number 4, actually Iapetus was just cruising along and it crashed into a big intergalactic bug.
Yeah. So a swarm of interplanetary locusts, it happens to the best of the moons.
Indeed, indeed. All right, well, it is time for the news trivia show. Are you 3 ready? And we're going to start tonight with Valerie. So here you go. A trio of researchers from CNRS, UMR, Tyndale House, and the Sorbonne University, respectively, have found what that might be the oldest blank from an archive at the Greek Orthodox St. Catherine's Monastery on the Sinai Peninsula.
So I'm pretty sure I know this one because Twitter gets me and shows me these kinds of things. And I believe it's a star map or a night sky map.
Yeah. And do you know who they think actually did it?
No, Twitter didn't give me that.
Oh, you got it right. It's the oldest star map known, from 129 BCE. It's believed to be the missing star map of Hipparchus, one of the ancient Greek astronomers who there's actually a satellite named after him, the Hipparchus satellite, which maps the position of stars. And it's believed that he created the very first star map. And here it is. The other really fascinating thing about this is that somebody wrote over his star map. They erased it and wrote over it because papyrus was so hard to come by back in the day. They literally just erased what he wrote over it. But these genius researchers figured out how to extract the original writing from the background and figured out that it was a map of the stars from Hipparchus. Not bad.
Very cool.
Yeah, nice job, Valerie. 1 point for you. All right, here's your second question. A new gas giant planet discovered around a cool red dwarf star has the density of what campfire amenity?
Okay, Twitter didn't give me this one, and I'm just going to take a wild guess. It's probably not right, but I'm going to go with marshmallows.
You got it. Yeah, it's a marshmallow. Yeah, very, very weird to find a gas giant around a red dwarf to begin with. We didn't even know if that was possible. Turns out it is, and it turns out it is really, really gassy. There's not much to this gas giant planet at all. It's got the density of a marshmallow, and here's an artist's idea of what it looks like. But nice job, Valerie. 2 for 2. All right. Go for the trifecta. Here we go. Okay, the closest blank was recently discovered at only 1,550 light years away.
Okay, this one I have no idea. There's a whole universe of things I could guess.
Do you want a hint? Do you want a hint?
I'll take a hint I'll lose a half point for a hint. I'll give up that half point.
Okay, so it could be in that blank spot and you wouldn't even know.
Okay, so that was my guess, and then I was like, but wouldn't that be catastrophic for our existence? So is it a black hole?
It's a black hole, but it's not a supermassive black hole like at the center of the galaxy. It's a stellar mass black hole. It's like 100 solar masses, but really, really close. Yeah, the closest black hole ever found to date. And that is the little point of radiation around the accretion disk that was actually, not around the accretion disk. I believe that was an X-ray source that was discovered to pinpoint the location of a black hole. But yeah, in the stellar neighborhood, 1,500 light years is nothing.
So for perspective, what are some other things about that distant from us? I mean, there's a lot of stuff that close, right?
Yeah, some stars. There are some nebulae that are a little bit farther away than that. There are a couple of nebulae just at around 2,000 light years away, but mostly just stars. Some clouds of gas, and that's probably about it.
Cool.
Yeah, it's pretty cool. Still a long way away. Traveling at the speed of light, it'll take you 1,550 years to get out there, but yeah, who's counting?
It's a matter of perspective.
Matter of perspective. But nicely done, Valerie. So 2.5 points for you. You should have just gone with your gut on that one. But you picked up a point earlier, just like everybody else. So that's 3.5 points for the lead. Nicely done. All right, Nick. Think you can do this? All three?
Well, it depends how many answers you show.
Nice. Touche. All right. What are scientists sparring about that may or may not be under the surface of Mars?
I think it's got to be like one or two things. I'm going with water.
Yeah, that would be liquid water. Yeah, so
Always talking about water.
yeah, the original scientists who published the sonar study several years ago showing that they detected liquid water under the surface, which was heralded as an underground lake on Mars, have now come out with a recent article debunking all of the naysayers who claim that it's not actually liquid water. And they say they've ruled out virtually everything at this point. But that the only way to be sure is to call Bruce Willis and to drill. So they will be sending a drill up to Mars. Actually, I mean, the plan is to do that eventually, but we're talking decades from now. This underground lake is like over a mile under the surface. So it's quite an ordeal, but that's the only way to be sure.
Elon has built all this technology for this. He's already built a boring company to drill holes, and he's got to go to Mars. So
this is totally his jam.
Yeah.
Yeah. But nicely done, Nick. And you got that one right.
My second guess would have been underground Martian colonies, which this could also be.
Indeed. Okay. Number 2. While not alien, what's that? There you go.
Oh, speaking of which,
while not alien megastructures as purported on the internet, the multiple concentric shells of expanding dust recently imaged by the James Webb Space Telescope have been explained by scientists studying Wolf-Rayet star WR140 to be the result of the fact that the binary star system has an 8-year elliptical orbit, and that the dust is being assisted by what strange electromagnetic phenomena?
I can't just straight up blame magnetic fields.
No, it turned out that their model didn't actually fit the concentric circles that were seen in the image. They had to tweak them a little bit, and they hadn't taken into account this effect, which is happening all over the universe, but very, very hard to get observational evidence of. But they got it here.
Huh.
And it, you know, I mean, it's about electromagnetic radiation.
Yeah. There's,
One of the
Ooh,
weird things that massless light does to things with mass.
oh, is this what,
Yeah.
particle wave duality? Something like
You're on the right
No?
track. Yeah.
that? Some sort of diffraction effect or what?
No, this is radiation pressure is what we're looking for.
Oh, radiation pressure.
The pressure that.
Oh, I was going to guess that.
It was on the tip of my tongue too.
Yeah.
Yeah.
That's what I thought. Yeah, this is real, folks. This is the pressure that light actually exerts on material objects. It's very, very slight, but when you're just talking about diffuse dust, the effect is noticeable. And yeah, the model that these scientists had come up with didn't quite fit the observations of the James Webb Space Telescope until they added in radiation pressure from this binary star system. And that's what did it. All right, Nick, we have one more for you. Oh, there's the lovely.
Yeah, that's a pretty picture.
Isn't that
Yeah.
amazing? Yeah. So the researchers had only seen 2 or 3 of these rings before. I think James Webb imaged like 16 of them or something. Pretty incredible. Nice job, James Webb. Okay, last one for you, Nick. Last week, the FAST radio telescope in China reported the discovery of the largest what around famous galaxy group Stephan's Quartet. It's all
black
around,
holes?
not black holes. It's
Oh.
way more diffuse than black holes. It's all around the galaxy group. They're like
Dark matter?
not dark matter. This is actually baryonic stuff that we know about. We can actually.
All right. What is what around? I know what a large thing is. It's around a galaxy group.
Yeah.
Uh,
It's
oh, dwarf galaxy?
no,
that would make sense.
it's simple stuff. It's atomic hydrogen.
Oh, just
Yeah, there's this like enormous cloud, the biggest ever cloud seen of atomic hydrogen, the 21 centimeter line, to be precise.
I don't know. I looked at the early universe, and that was a big.
I know. You did microwaves. You're not a centimeter guy.
All right, fine.
But nicely done, Nick. A valiant effort. But Stephan's Quartet is one of my favorite interacting galaxy groups. It is so cool, and you can see the big atomic cloud in red there around those galaxies. All right, Danny, you're up. Are you ready for this?
I guess so.
Okay, Valerie is still in the lead with 3.5 points. Last week, this astronomer who commanded NASA's first spacewalk died at the age of 93.
Oh no, I know this. I read an article about him.
You know this.
Yes, and I'm blanking on his name. I don't remember.
Google it.
Yeah, really, no, I never do that when I'm on here. No.
It's okay. I mean, I gave you guys one of the answers, so like, why not?
Oh, no, it's okay.
It's Jim McDivitt.
That's right. Okay.
Yeah, one of the yeah, I mean, he was one of the pioneers. He was on Apollo 9 doing some of the early test work of all the stuff that eventually paved the way for the moon landing. And interestingly enough, I read part of an interview from him. So when he found out that he wasn't going to be one of the first 2 people on the moon, he decided to resign from the astronaut corps because he said he wasn't interested in being 3rd or 4th, which was shocking to me. I would take like 28th or like 3,000th of to get to the moon. I'm not so concerned about the numbers, but apparently that was a big deal back then. So yeah, he commanded the first NASA spacewalk, flew several missions, did a ton of work for NASA after the fact, but never actually got to the moon, unfortunately. But yeah, did a lot of work. And here he is, a great shot of him actually up in Apollo 9. This was there was a note on this image that this was before astronauts were allowed to bring shavers with them. And so it started on Apollo 10. So like the first 9 missions, there were no shavers. So all grizzly guys coming back. Okay, here we go. Yesterday, a new NASA study commenced to study UAPs, which stands for what?
I don't remember. I need a hint.
The hint is we've already talked about this a couple of times before the show and during the show. Yeah.
What was that, Nick?
So Valerie, were you on when Valerie was talking about the highway that she drove on? Did you make?
No.
Oh, Valerie drove on the ET highway.
Oh, so
Yeah, you got
UAP.
the part.
So like,
Yep. Keep it
so
going.
unidentified.
Yes, you got a third of a point. Up.
Huh?
Yeah, it's an A. Think words that describe the up above.
Atmospheric.
You're so close. You're so close.
Altitude.
You're getting there.
You guys are killing me.
It's
What was that?
aerial.
Oh.
You still get a third of a point. Unidentified aerial. What's the P?
Phenomena.
Phenomena. You got 2/3.
We would have all gotten it together because I didn't know what the U was, and you knew what the U was. So.
Unidentified aerial phenomena, which I didn't know this. This is the new PC term for UFOs. Yeah. Apparently NASA is trying to get away from talking about UFOs. The new name for unidentified flying objects is actually unidentified aerial phenomena. Here's the classic one from the Navy pilot a couple of years ago. But yeah, they've actually commissioned a whole group of people, including an astronomer who I got to meet, David Grinspoon. Very excited to see his name on the list. And they started yesterday. It's a short study. It's like 9 months, but they are going to basically look at all of the data and try to make sense of it, which I think is pretty cool.
So I have a question. I have a follow-up question. Is the idea of moving from flying objects to aerial phenomena that like we shouldn't assume they're physical objects, like some other cause might make this weird black dot appear again?
Or maybe they're not flying. Right?
I think that's it. I think
They could be hovering.
I think it has something to do with that. I think the assumption is that it's broader than just spaceships.
Okay. Okay.
Yeah. You tell me, Valerie, did you see the phrase unidentified aerial phenomena anywhere on the ET highway?
Well, no, but they wouldn't put it there because that's not the term, people don't go for that. It's got UFO everywhere and ET. That's what people want to see.
What's a UAP?
It makes me think of something like the Aurora Borealis,
Right,
sort of
like a
magnetic
non-physical object.
Yeah.
Yeah.
All right, Danny, we got one more question here.
Okay.
And this one occurred earlier this month, but we didn't put it into the show last time, and I really wanted to because I read his interview. It is really, really interesting. So earlier this month, William Shatner finally got to go to space on board Jeff Bezos' Blue Origin, but unexpectedly, Shatner reported being filled with a what?
I don't know, like fear or sadness?
It's supposed to say it's sadness. It's
sadness. Yeah, that's right. I read that.
Willed is a typo. Our apologies on that. Okay. Being filled with an overwhelming sadness.
Yeah.
And that's called the overview effect. And it's been experienced by several astronauts. But what he said was that he expected to feel this, this elation and excitement, but it wasn't at all what he felt. He looked down at the Earth and then up at the blackness of space and was just overwhelmed with sadness. And he wrote a lovely article about it. And if you haven't read his article, it's worth taking a look at. It's very, very moving. Well, I think Valerie is our champion this week. Nicely done, Valerie.
Thank you.
You are welcome. And it is time for our guest spot. We're not going to take a break because we're not doing our OBS overlay right now. But please welcome Hannah Fritza from the University of Utah Astrophysics Department. Hannah, step on the stage here.
Hello.
There you are. All right. Hannah, thank you so much for joining us. We really appreciate you being here.
Thanks for having me.
Yeah, we're gonna skip that little segment there because we're already late on time. But yeah, it's really nice to have you. And we like to start all of these guest spots with the same question, which is, what's the one question that you wish that everybody would ask you, but nobody ever does?
So you warned me that this was the starting question. About 2 weeks ago, I had my joke answer locked in, which was going to be, would you like to play a D&D campaign? And then I recently increased the number of D&D campaigns I play every week to 3. So that feels like maybe a little much at this point. Instead, I've gone for a slightly less jokey answer of, would you like to come give a talk, or would you like to come be on the show? Because you guys are actually my first invited talk or like public outreach outside of the university. So it's very exciting for me, and I like
We
them.
are honored. We are honored. We are happy to be your first, and we'll get to say we knew her when before she got her Nobel Prize and
Before her H index went way up.
Yes.
before her H index was off the charts, and she became a Nobel laureate, a 2-time winning Nobel laureate. We had her right here on the Astro Show.
The dream. We're setting the bar really high. That's ideal. Yeah.
Well, Hannah, how did you get to where you are today? What was your path that led you to becoming an astronomy graduate student?
I was very much like one of those nerds in high school who like really pretty early on decided what they liked doing and then kind of did just that forever. So I, at some point in high school, I don't remember exactly when, started reading just like a bunch of, there's like I feel like tons of like astronomy books and essays that are written for non-astronomers or for amateur astronomers. And I was just like getting really into all of those and thinking astronomy was really cool. And then I originally grew up in California, and the UC system has these like summer programs for high school students that happen at some of the different like University of California campuses that are like really like science specific. And they had one for astronomy that I think, if I remember right, was at UC Irvine. And so I went and did that just to be like, I hope I do like this, because so far that's kind of my one plan for what I like to do. And thankfully I did have a really good time. And so when I got to college, I specifically looked for colleges that had like astronomy programs, because I didn't love physics in high school. I didn't like physics for a really long time, actually. I think it's not uncommon. I like it a lot more now. I think like over time, as I've learned more of it, it's more appealing to me. But yeah, I did a bunch of astronomy in undergrad, and then took about a year in between undergrad and graduate school. And now I'm in my 4th year of grad school, and so far I still like it. So it's holding on well.
That's awesome. Very, very cool. So what are you studying right now?
Yeah, so I am studying the galaxy that's on the screen at the moment, M31, which is also the Andromeda galaxy. It's our nearest Milky Way type galaxy. So it's our nearest sort of spiral galaxy neighbor. There's some closer little like dwarf satellites that we have hanging out near the Milky Way, but Andromeda is like our closest Milky Way type. And so there's sort of a difficulty in studying the Milky Way, and that we live in the Milky Way. And so we can only observe it in certain ways. And there are parts of it that we can't see very well with different types of light, because there's like gas and dust, or like the center of the galaxy that are in the way. And so because we have this sort of Milky Way-esque galaxy nearby, we look at that as sort of a proxy or a lab environment for the Milky Way, where we can see the whole thing at once and get a better idea of like how the galaxy behaves. And so I look specifically for X-ray binaries in the Milky Way, which are these binary star systems where you have two stars orbiting each other, and they become an X-ray binary when one of those stars goes through its stellar evolution. It like ends its lifetime as a star and becomes a black hole or a neutron star. Those are then detectable in the X-ray part of the light spectrum. And so I look for those and I try and characterize that non-star piece, the black hole or neutron star, and determine which one it is and like how many of them are in the galaxy and things like that.
Very cool. So, I guess like the $1 million question that every astronomer gets asked about what they're studying is like, so what? Like, why do we need to know about these X-ray binary systems where these, stars are becoming black holes or neutron stars? What do we learn there that that helps us understand the universe better?
Oh yeah, a bunch of stuff. I mean, for one thing, black holes and neutron stars are just really cool.
Yeah.
So it's nice to find more of them. That's very exciting. But also specifically when it comes to like X-ray binaries, because the neutron star, the black hole, was originally a star that went through this life cycle. It tells you a lot about what that galaxy maybe looked like before. If it's a newer system, which you can tell especially from its sort of companion star, and get an idea of like when star formation might have happened recently in that part of the galaxy. And then the population of X-ray binaries in a galaxy can give you hints for a lot of other things about it that you wouldn't necessarily associate with a black hole or a neutron star. So it can tell you about not only the star formation that's currently happening, but maybe where stars formed in the galaxy before. It can tell you about the metallicity of a galaxy. So astronomers like to call pretty much all elements metals. We use that,
right?
Yeah, basically hydrogen up. It's like, yeah, metals. But the metals that are heavier than iron, or the elements that are heavier than iron, don't form naturally in stars because they don't have enough sort of energy from fusion going on to form anything past iron. So anything that you get after that typically comes from a supernova where you have a bunch more energy than the star creates normally. And you're going to have a supernova in order to produce a black hole or a neutron star typically. And so the population of X-ray binaries in the galaxy can also tell us about its metallicity, or how much metal is in the galaxy. And we recently, as a field, not me personally, have detected gravitational wave sources. So we can see when, say, two black holes, or a black hole and a neutron star, or two neutron stars that were in this sort of mutual orbit binary, like spin together, they produce these gravitational waves. And while X-ray binaries aren't going to do that, if the other star, the remaining star in the binary, turns into a black hole or a neutron star, those could then spin together and merge. And so getting an idea of the population of X-ray binaries in a galaxy and in the universe can give us an idea of how many of these sort of gravitational wave sources we might expect to see, because eventually some fraction of them should become gravitational wave sources. So there's a lot of cool things about X-ray binaries that aren't just like, I found a black hole and a neutron star, but I think that part's really fun too.
Yeah, that is super cool. Thank you for sharing all that. I know that James Webb, does all its imaging in the infrared, but is there any possibility of observations from James Webb being used to somehow interface with the work that you're doing on these systems?
It's my initial reaction is I'm not sure. I would say it's possible. I think a lot of the goal of James Webb seems to be looking a lot more at the early universe.
Yeah.
And unfortunately, when in the X-ray part of the light spectrum, we're pretty limited on how far we can see
Right.
before it starts to get a little dicey, or it's so far away that like the light gets redshifted out of the X-ray spectrum again. And so now we're in other parts of the light spectrum. But I think James Webb is going to see a bunch of stuff in the really early universe that could be really interesting for black hole science. Like I think one of the potential science goals of James Webb is to see if it can see these things called population 3 stars.
Right.
Yes, and those are somewhere. So part of my older work in undergrad was looking for intermediate mass black holes. I'm not doing that now in Andromeda, but I've done it before, where there are these sort of black holes that are in this mass regime that's between the black holes that you get from stars and the supermassive black holes that you see at the centers of galaxies. And not everybody agrees that there should be intermediate mass black holes, but I think it would be cool if there were. But basically there's this problem where like there's this whole area of mass that we don't see black holes in. We see like little ones and big ones, and then we don't really know how the big ones got to be as big as they are. And so one of the ideas is that you can get these intermediate mass black holes that are sort of in the mix in the middle, and that those might have happened much earlier in the universe because of population 3 stars, which could be, in theory, they could be more massive than stars now. And so if they were more massive when they formed black holes, they could form more massive black holes and maybe solve this problem of like this middle area that we don't really see. So I think that would be super cool.
Yeah, so it sounds like your vote is that there actually are, or maybe were, intermediate sized black holes at some point in the universe evolution.
I think so. I don't know. I think it's I don't know if that feeling on my part is entirely like based in full science. It's more just like this feeling that I feel like there should be something in the middle.
I mean, gut feelings work. That's
exactly. Like it's definitely more of a gut feeling, I would say, than anything else. But there are sort of candidate intermediate mass black holes out there, things that are really bright, where we're like, okay, maybe it's because we don't entirely understand like how this emission is working, or we're making some assumptions that aren't quite right. But also maybe it's just a more massive black hole and we found one that's in the middle. So there's like a handful of candidates out there that I hope are actually candidates, but it's hard to say.
Nice. Well, do any of the co-stars have any questions for Hannah?
I have a comment and then a question. I will say, because we just found a marshmallow super red giant orbiting, whatever, like things we don't think that can be happening in the universe. We find them all the time and we're like, apparently that's a thing now. So I am going to be on the side of intermediate mass black holes with you. There's no reason to think they don't exist. We just haven't detected them. And that's just a matter of the techniques and tools we're using. Anyway, I would love to know what your favorite pair or binary system that you've, like, what's your favorite one that you found or studied?
Oh man. I mean, at the moment, I'm still very much like in progress. In fact, right now I'm really in the weeds of writing a paper about everything that I've been looking at so far. But one thing I'll say, which I have to look at it some more and make sure that I agree, and it may or may not be right. So I will say, a word of caution that this may not last under further scrutiny on my part. But we maybe have one of the sources that we're looking at. We feel pretty confident that it's a black hole, at least at the moment. I have to look at it a little more deeply. What I'm doing right now is a very rough classification of things, and then we sort of pick out sources that seem interesting and look at them more in depth. So this is a rough classification. We think it's a black hole. And also we think it might be in a globular cluster, which would be really cool because we don't see a lot of those. The sort of general idea is that you can form black holes that might then fall to the center of globular clusters, but that a lot of the time that doesn't happen because they get sort of kicked out in the process of forming by everything else that's in there. So if we did find one in there, it would be awesome. So right now that's my favorite one, but I have to dig into it a little more and make sure that I really believe that both of those things are true, that it is both definitely in a cluster and definitely a black hole. And as of yet, I haven't convinced myself enough to write it down yet, but so far so good.
Well, I hope it turns out to be.
Me too.
Anybody else?
Yeah, just because most of your observations are in the X-ray. You said with NuSTAR, which is a wavelength I'm not at all familiar with, but I do know the only way you're going to look at X-ray is satellites, and that's what's up there right now, I assume. And I think that's also a good question: is what's on the horizon? I think, are there any new ones coming up, or is it pretty far out right now?
I think it's new in the astronomical sense, maybe. I think, as astro telescopes, after they get approved, there's always like a nice long chunk of time before they actually go anywhere. James Webb is a classic example. In like the recent, there's this like decadal survey in astronomy where they sort of look at everything and sort of identify all kinds of things about the field, but one of those things is sort of what might be interesting telescope-wise to do in the future of astronomy. Sorry, my dog is being loud.
That's all good.
She loves to yell. But in that recent survey, they sort of decided to emphasize a lot of these things sort of called probe class missions, which just means that they're slightly cheaper than your James Webb. Yeah, slightly cheaper. Again, cheaper in the astronomical sense, which is still far, far more money than any single human being could reasonably make, unless you're maybe like a Bezos or something. But there are some, I think there are two sort of semi-competing, semi-not competing probe class X-ray telescopes that people have suggested. And so I actually just recently joined the planning committee for one of them, which would be really cool. And it could see a little farther away, so its resolution is a little better. And then also it would see in a slightly expanded spectrum, which is really nice. So there's potential good stuff in the future. If that got approved, it still wouldn't launch for another like 10 years or something. So it's definitely like, you know, astronomically new potentially, but definitely not new in the sense of what any sort of reasonable
That's
person
on the
would
horizon,
consider on
you
the
know.
horizon. Yeah.
Something to be excited about.
So there's hopefully going to be at least one cool new astro telescope in the next 10 years. I'm keeping my fingers crossed. I'm optimistic.
Nice. And I think I remember seeing that the data you're using right now come from the NuSTAR telescope. Is that right?
Mm-hmm.
Nice. Will you tell us a little bit about that telescope?
Yeah, NuSTAR is awesome. Especially if what you're doing is trying to classify X-ray sources. And especially if you're trying to differentiate between black holes and neutron stars. So NuSTAR is particularly nice because it sees in a range of like 0.1 keV to 100 keV. And that is a nice broad range of energies. But most importantly, it sees above 10 keV. So that 10 to 100 is like the crucial range for me. And this is because the difference between black holes and neutron stars in the X-ray is most apparent sort of above that 10 keV line. And it's because of the way that they take on material and sort of what they are like as objects in general. So both of them we see in the X-ray because they're slowly taking on material. So they're accreting stuff usually from their like companion star. The outer layers are sort of falling onto the black hole or the neutron star, and they're forming this accretion disk. So this like nice sort of thin disk of material as they fall onto either the black hole or the neutron star. And the difference between the two comes into the fact that a neutron star has a surface. And so as things fall into a black hole, there's a point where like they don't come back out again and we don't see them. But as things fall onto a neutron star, as it hits it, it can still, that surface can like reflect away some of the energy from the inside. And so in both cases, the accretion disk has this sort of like, and I'm going to use a lot of hand talking here, I apologize in advance.
Great.
It has this sort of like hump shape or this sort of like parabola shape almost, that's the disk. And then in the black hole case, there's this sort of interior area that's like very hot gas that forms in the sort of latter half of the spectrum, a flatter sort of line shape. And so you get this like initial hump and then a nice little like line off to the side. And in the neutron star, the same things are present, but there's also this little bit of reflection off of the surface. And so the sort of hump part is not as like peaked, it's sort of broad like this. And where it tends to be broad or broader, where the shape tends to differ is above 10 keV. And so the way that I do my characterizations is that I split up the energy that we're getting into an area that's sort of like in this, we call it the soft range, but the lower energy range, the sort of medium energy range, and then a high energy range that's up above 10 keV. And I look at how much of the light that we got from the sources in each of those sort of areas. And the ratio between those areas is going to be different for a black hole and a neutron star. So a neutron star is going to have a lot more of this sort of up above 10 keV energy compared to the lower energy bits than the black hole does, because it still has the rest of this hump continuing on past that point. The black hole, by the time you get there, has sort of mellowed out and the little hump part is over, and it's just kind of slowly trickling down in energy in the high energy side. And so the ratios look different. And so there's this little plot that's on the screen that's very colorful. But over the one that's sort of on the top left is basically a plot of color. So one of the colors is down on the x-axis, the other color is on the y-axis. And the difference between these colors and their ratios can give us an idea of what kind of source it is. So the neutron star is going to have a bunch of this like hard color, this high energy X-ray emission. And then black holes are going to have, maybe a little bit of that, but mostly stuff on the lower end. And so the fact that NuSTAR can see above 10 keV is like really huge for doing stuff like this. Because if you're below there, it's still, you're seeing sort of the hump, which is nice, but they both could have that. So it's a little harder to tell between the two if you can't see above 10.
So the probe class you're working on, what's that energy range looking at?
It's similar. I think it's up to about 150 keV, so it would go up higher. But what's most exciting about that one is that its resolution is a little bit better. So NuSTAR's, I would say one flaw is that its resolution isn't good. And so things that should look like points kind of look like blobs. And what that means is that if you're looking at a galaxy that is not like a nice nearby friend like Andromeda is, if there's a bunch of sources that are all next to each other, their blobs overlap a ton. And so it can be hard to tell like what light is coming from where. And so the telescope that I just joined the sort of planning committee for is going to be better with resolution, and therefore we'll be able to see galaxies farther away and start doing comparisons between like what we see in Andromeda, what we see in the Milky Way from what we can see of the Milky Way, and then also what we can start to see of galaxies farther away, and sort of make sure that they all agree with each other as we think they largely should.
What's the name of that mission?
It's called HEX-P. And I'll also say I just, as of like a day or two ago, joined that one. So I'm not totally up to date, but those are like the broad things that I'm the most excited about for it.
Yeah. NuSTAR is worth looking up because this is just nerding out about optics, but X-rays are weird because they like to go through materials. And so getting them to reflect is challenging. So you have to have a grazing incidence, which is just a kind of weird mirror that's barely at a slant, and then a bunch of them to bring them to a focus. What that usually means is very long focal length. So it's this really weird looking telescope with this giant boom out front, 30 feet long. It's got the mirrors 30 feet away from the camera effectively just to be able to get that to work, which I've seen a few X-ray telescopes. The ballooning I do, there's one been around with, but yeah, they're really weird looking.
Oh yeah, they look crazy. They like don't look anything like you would expect a telescope to look like. There's no, like you said, there's no singular flat mirror. It's like a bunch of them. It looks like a bunch of stacked cylinders. It doesn't look like it should be able to detect anything. Like they look fake. NuSTAR is also fun because the that like long distance that you're talking about between the detector and the mirrors is like totally uncovered. Like it's just like, essentially a boom that they can extend to get it all the way out to this distance. But it just like looks like, a part of like a moving crane basically. And so what that means is that sometimes, and by like actually all the time, you get a bunch of background that not only is like your sort of typical telescope background that's like focused by the telescope mirror, but you also get background that's just like casually flying in on the sides because it's not enclosed. And so someone else in our group at Utah does really extensive modeling of just like the NuSTAR background to make sure that like everything that we're looking at is what we think we're looking at, because there are so many areas where you can get like weird extra signal in the data that you have to account for. And so the plots of X-ray backgrounds look like absolutely nuts.
Very cool. Well, we're getting close to being out of time, Hannah, but I'd love to know what your future plans are. After you finish up your graduate degree, what are you thinking?
I would really like to end up somewhere that has I guess, like a college or university that has a fairly even split in terms of its focus between like teaching and research. So my undergrad university is Wesleyan, just like tiny. It's in Connecticut. It's a little liberal arts college. Their astro department is fantastic. I really recommend it. Utah's is also rad. But they did almost entirely undergraduate teaching. They had like 2 grad students every year. They just have a master's program. They didn't have a PhD program, at least in astronomy. And so a bunch of the focus was on like teaching and undergraduate research. And I really like that. I got to teach for the first time once I got to Utah. And I really like it, but I also still really like doing research. So I kind of want to like merge those as much as possible. And so the idea of doing mostly like undergraduate sort of education and research is really appealing to me. And I also, I realized I do like physics. And I feel like in college, I really didn't like physics and intro physics. And now I think it's really cool. So I would love to teach like mostly like intro physics and astronomy classes. I think that they're really fun. You get like a really wide breadth of people. Like you have like some people that are like pre-med and they're like, okay, I'm going to do physics so that I can learn about like, you know, how muscles can help move parts of the body and like how torque works. And then you also have like the little astro nerd kids like me who are like, I'm learning physics just to do astronomy. And then people who really like physics, and then like everybody in between. And I think that that's really fun. So I would love to, you know, after my PhD is done, you know, either do a postdoc and then go into like a professor position somewhere like that, or go straight into a professor position if somebody will have me. So we'll see.
Well, best of luck to you. And we really appreciate you giving us your time this evening. So thank you so much for that. We've got a thank you gift for you, and our operations director, Maggie, will connect with you to give that to you.
Awesome. Yeah, thank you for having me. This was really fun.
Yeah, it's been a blast. And as always, thanks to all the co-stars. We would not have the show without all of you. So thank you so much for being here. All the other folks behind the scenes, Maggie, Wyoming Stargazing Board of Directors, and all of you out there who will watch this show on YouTube. We hope you enjoy it and that you join us again in a couple weeks. Until then, be well and don't forget to look up. We'll see you next time. Bye.